this talk by announcing that, so I'm at Auburn University, and we're going to be hiring several tenure-track professors this fall. One of those searches is targeted at topological data analysis. So for those of you out there that are postdocs getting ready to, or polishing up your applications right now, keep us in mind. It's actually a beautiful campus, big school. We got about 30,000 students, about 120 graduate students. And I just moved here about 6 months ago, and we liked it a lot. Anyhow, so keep this in mind. So the topic of today's talk is algebraic tools for multiparameter persistent homology. So what I've got 4 parts to the talk. I'm going to throw them up there in a second. The motivation for this is a question of Carlsson-Zomorodian in a paper about a decade ago called Theory of Multidimensional Persistence. They introduced the theory of multidimensional persistence, and of course, the starting point is that for persistent homology, we know that the barcode is a complete invariant. So we have this beautiful, easily sort of visualized description, and that all comes from the fact that persistent homology is a module over a principal ideal domain, where in our, I don't know, first semester graduate algebra class or upper level undergraduate classes, we teach the students about the decomposition theorem that every module over PID is it decomposes a direct sum of some free copies and some torsion bits. Torsion bits being the short bars and the free parts being the long bars. So, so we have that, of course, and I've got 2 quotes that are the motivations for this talk from the Carlsson-Zomorodian paper. The first quote is that there exists no variant or version of the barcode in higher dimensions. So once we pass from a filtration that only has 1 parameter, and I'll have a picture up, I'll share screen in a second, but once we have a filtered topological space where the filtration depends on more than 1 parameter, so perhaps filtered in 2 directions or 3 directions, you don't have an analog of the barcode. And the second quote is, we still desire discriminating invariant. So that's the motivation, is what is the right analog, I guess one would say, of the barcode for higher dimensions. So that's part 1. And now I'm going to do 1 more Blackboard bit before I do a share screen, and then we'll come back. So this talk, so the first thing I should say is this talk is this is joint work with Heather Harrington, Nina Otter, and Ulrike Tillmann. It has actually been published, so it came out last year in SIAM, the SIAM Journal of Applied Algebra and Geometry in 2019. And the results, so I want to say what the result is. So here is our candidate for the answer to the question of Carlsson-Zomorodian. And it involves, and this is what the bulk of the talk will be, is a discussion of methods from commutative algebra and algebraic geometry to answer their question. Our candidate for this is the following theorem, MPH, an MPH module. So MPH is going to stand, and we're going to not call it multi-dimensional, but multi-parameter, because there's several parameters involved. Multiparameter persistent homology module is supported. I'll talk about what support means on a union, let's just say on a coordinate subspace arrangement. So one of the things that I enjoy working on in topology is hyperplane arrangement. So hyperplane arrangement is just a collection of hyperplanes. Here, instead of hyperplanes, we have subspaces, but they're coordinate subspaces. So what that means is one might visualize for a bifiltration, if there's 2 parameters, we might visualize the MPH module as being some number of copies of the plane. So this is a plane, plus some copies of lines, which are the x-axis, plus some number of copies of the y-axis, and then some number of copies, m and p, plus p copies of the origin. So some planes, some lines, and some points. But these are more than just any planes and lines and points. These are actually coordinate lines, planes, and points. So, and then what's the right analog? So how do you translate this picture into the persistent homology? So the difference is that here, these are essentially like, and I'm using this loosely, but these are like the free summands. If we're in two parameters, copies of the plane are somehow full dimensional things. So these are like the persistent full dimensional summands. Over here, for the points, these are like the torsion bits. They die in high degree. But these are a new sort of beast right here that we see. These are lines. So they don't die in high degree. They are persistent, but they're smaller dimensional. This is a supersized guy. He went to McDonald's. He's full dimensional. He's fat. These are skinny components, but they persist to infinity. So these are a new version. So that's sort of our candidate for an answer. The other point I should say is that all of this information about the number of components can be encoded in something called a multigraded Hilbert series, which I think is a nice way to package all this data. So that was part one of the talk, which was supposed to be 5 minutes, and I'm already 5 minutes behind. The other thing I want to say is there's one thing that's going to be a cheat during this talk. So, and that is that when we're dealing with topological data analysis, our starting point is point cloud data. We then fatten the points and then eventually end up with a filtered topological space from which we obtain a filtered simplicial complex. So the cheat part of this talk is that I'm not going to blur my eyes. So to go from the point cloud data to the filtered topological space, we blur our eyes and sort of things get fat. Our starting point, our jumping off point is a filtered simplicial complex. So now I'm going to share a screen with an example of this. So let's see. And what do I want to do? Hang on a sec here. Let's get that. And share the whole screen. So this is, I want to talk briefly about the motivating example so we're all on the same sheet of music. So this is our starting picture. So this is a bifiltration. So we have two parameters. I have a parameter that I'm going to call x2 that moves, oh, I can use this little blue dot, can I? No, that's not, that's me. Okay, so I have a filtration that goes in the x2 direction horizontally, and in the, I'm sorry, the x2 direction vertically, the x1 direction horizontally. So let's look at what the differentials are in this, for this bifiltration. And the idea is that this is just ordinary old simplicial homology, except that we have to decorate it to keep track of the degrees where things appear. So I want to look at the first, and this is the first boundary map. So this is going to map me from edges to vertices that we see at the bottom of the page. And if we look at the first column, if we look at our simplicial complex, we have 6 vertices and we have 8 edges. So I'm going to have a 6 by 8 matrix. So I have 6 rows. The rows are labeled A, B, C, D, E, F for our 6 vertices. I have 8 columns labeled for the 8 edges. And I want to look at the very first column, which corresponds to the edge AB. So audience participation, which is of course impossible. Everybody should unmute. I will, at some future point where we're all in not virtual, but in a real space, I will buy the first correct respondent a beer. What multi-degree does the edge AB appear in? So you can see the vertex B appears in degree 0, 0. The vertex A appears in degree 1, 1. Where, in what multi-degree? For beer, a nice IPA, nice crisp IPA, maybe in Colorado. What do you think, Henry? Where does AB appear?
Oh, we need a non-organizer to answer. Come on.
A non-organizer to answer. I'll drink the beer myself if nobody answers.
I have some graduate students on the call from Colorado. Come on.
Come on, grad students. Everybody, all the grad students should be wanting a beer.
2, 2?
Yes, 1, 2. Was it 1, 2 or 0, 2? It's 1, 2. So if you look, right, so if we look in degree 1, 2, that the vertex A, which is the very top vertex, appears in degree 1, 1. And if you go one step up to degree 1, 2, you see that the edge AB is there, right? So it appears in degree 1, 2. So what we've got is that edge AB, when I do the boundary map, it goes to A minus B. But I have to take the grading into account. So to get to the A vertex, I drop down 1 unit. That's 1 unit in the x2 direction. So that's why in the 1, 1 position of our matrix, we see an x2, because I have to drop by degree x2 to go from edge AB to vertex A. Similarly, to go from edge AB to vertex B, I have to drop 2 units vertically and 1 unit horizontally. So that's x2 squared times x1. So it's a Knight's move, right? And so that's why we see the minus x1 times x2 squared in the second position of the matrix. So that's how this differential works. So it's really quite simple. So the point is, it's just usual simplicial homology, but we add in these monomials to reflect where things are coming from. So I'm going to unshare my screen now and go back to the board. So let me stop for a second, take questions from moderators, or I guess I can look at, I'll let you guys yell at, the moderators can yell the chat stuff at me. Anybody have any questions on what the objective is here? So I have a sequence of maps like that. So we had this, this matrix, which was the ordinary simplicial map, but decorated with monomials. And we have a sequence of such things. That was just from edges to vertices. But there's a similar, and if anybody wants, I can share the screen and do it again, but there's similar things. And so we want the homology of such a set of objects. And of course, if you're a commutative algebraist or algebraic geometer, when you see something like that, matrices with polynomials in it, you get excited because that's bread and butter for us. So that's part 0 and 1 of the talk, which is the motivating question and the example. So now this is sort of the heart of the talk for the next 20 minutes. I'm back on track. I'm going to talk about the tools from algebra that are going to go into understanding this question. So this is.
Can I ask you a quick question first?
Yeah.
So before getting into the details, could you maybe give an intuitive idea of what information is being left out when you, since there's no barcode, there's no sort of complete clean invariant, what information is potentially being dropped in the discriminatory invariant that you
That's
studied?
a great question. So it depends on how much dropping you do. If you go to, so I said we could encode everything in the Hilbert series. The Hilbert series is packaging all the dimensions, and so essentially what one should think of is this sort of the multigraded. So a singly graded Hilbert series is so if I have a dimension. So let's say I have. I don't want to go too far off track here, actually. So what's being left off is, roughly speaking, how the pieces interact. I guess I would say that's a very rough description of it. And so what we're going to see here when we do the algebraic tools, in fact, you'll see part of that when we do the algebraic tools here. So there are interactions between the pieces, and roughly speaking, it's almost like, here's a bad analogy, but it's not completely bullshit. There goes my PG rating, right? So it's like a Meyer-Vitouris thing, right? So Meyer-Vitouris, we have direct sums and intersections and unions, and somehow what we're plucking out is 2 pieces. We're interested in the union, right? And so we're picking out the direct sum, and the intersection is how the pieces are gluing together, how they're interacting. And so it's there, but it's not. If you package things as a Hilbert series, it's hard to pull it apart in some sense. So that's a rough description or a loose analogy. It's not perfect though. And I guess another answer would be, even if I take the multigraded Hilbert series, there's various modules that have the same multigraded Hilbert series, and sort of in coarse terms, they have the same behavior, but it's this how they interact, how their components interact and intersect that we're missing. All right, so the next part of the talk, I would like to give a better answer, but in the interest of time, I think it's better to move on. So the next part of the talk is going to be our algebra boot camp. So this is something that I hope is novel for folks there. This is also something that I probably would spend 2 weeks on in a graduate algebra class, and we're going to do it in 20 minutes. So this is hopefully anybody who won that beer is not drinking it, or maybe you should be drinking it now. So I want to talk about associated primary decomposition. associated primes, and localization. So these are our 3 bullet points. And the rough idea of this is, how do you visualize? So here's sort of the motivation is, how do you visualize, or how do we, team effort, how do we visualize a module? So the first thing to do is to think about, I mean, from a topological or geometric perspective, we know that the standard sorts of algebraic objects that we might have is a vector bundle. So here's some curve C, and if I take a line bundle, a rank 1 vector bundle on C, I would draw a picture, or we would draw a picture like this. So here's a line bundle on C. And so essentially, what we're going to do is sheaf theory. And so a sheaf is exactly a sheaf. If it's a locally free sheaf, it's going to look something like this, but sheafs don't have to be locally free. And so the idea is that we're going to have different fibers. So we don't have uniform fibers, and so it's not a perfect analogy to a vector bundle, but that's roughly what's going to happen here. So that was the loose analogy. And now I want to put some actual honest math. So I haven't done any sort of definitions or theorems. I won't prove theorems, of course, but I will give definitions. So here's our first theorem. If R is a Noetherian ring, and here what we should keep in mind is, of course, for us, the paradigm is polynomial rings over a field. So I'm going to work with a field, well, let's say K is a field, and I'm working with the ring R, which is K of x1 up through xn, for example. This is the paradigm of a Noetherian ring. Of course, the point is that in persistent homology, we're dealing with n equals 1, right? We're dealing with a module over a polynomial ring in one variable, which is a PID. And this can be, this is typically R for us. So, and that, for the purposes of this talk, if you prefer it, you can think of our field as R. So a Noetherian ring of this type. So if R is a Noetherian ring, O and K is field, so we have this, then any ideal I contained in R has a primary decomposition. So what that means is that I is an intersection, 1 through M, different than my N here, of Qi. So I can write this I as an intersection of ideals Qi, where Qi is primary, and what that means is that it's almost like a prime ideal. So a prime ideal, of course, if P is a prime ideal, this means that if xy is in P, then either x is in P or y is in P, right? So that's prime ideal. We all remember that from our basic algebra. So primary means that if xy is in Q sub I, there's an asymmetry. Either x is in Q sub I, or y to the m n p is in Q sub I for some p. All right, so what this is saying is that in a Noetherian ring, an ideal doesn't decompose as an intersection of prime ideals. So again, somehow the philosophy of all of math is about decomposing complicated objects into simple parts. In representation theory, we have representation, we decompose it into a bunch of irreps, right? When we're dealing with algebra over a polynomial ring, an ideal is the paradigm of a type of module over that ring. This is sort of the simplest module. It's a submodule of the ring itself. We want to decompose an ideal into somehow constituent pieces that are fundamental. And so the most fundamental objects would be prime ideals. These are not prime, but they're close to it. And so the last definition I want to remind you of is that we say a radical of an ideal, or an I, the radical of I is the set of F, such that F to the P is in I for some P. So the radical of an ideal is just the set of everything such that some power is there. The reason I mention this is because it's clear from this definition that x, y, and qi means x is in qi or y to the p is in qi. I'm checking that I'm not on the board. That means that the radical of qi, so the radical of qi is prime. And when if we have the definition, if I is equal to some intersection, I equals 1, 2, m of qi, then the radical of the qi's, which are pi's, are called the associated primes. So what we're going to do basically, and this is going to work for modules too. So the idea when we're talking about visualizing a module, we're going to turn the module into a sheaf. We're going to look at the stocks. So again, this is my loose analogy with a vector bundle, which was that over a point of the base, we have a fiber. Here, when we look at a point over the base, our base is going to be some affine space. And we're going to look at the fiber over a point, and it's going to be some localization of the module. And so this localization is going to be an analog of looking at the fiber of a vector bundle. And so these are the associated primes. And now, let's see. So we've talked about primary decomposition associated primes. We need an example. So this is terrible. I've gone 25 minutes with no serious example. I mean, we had the example of Carlsson-Zomorodian. So let's do a quick example. So example of primary decomposition. So let's let I equals x squared minus x, xy minus x, contained in R of xy. Polynomial ring in two variables, here's some ideal. So when we look at the corresponding variety, equals the set of, and I'm being a little cavalier here, but it's okay. It's the set of points in R2 such that f of p is 0 for all f in I. This is called the variety. It's simply the zero locus of the set of all polynomials in this ideal. So this variety, if I drew, well, just draw the picture in R2. So here's R2. I can see right away that this is hard to do in general, but for this toy example, I can see, well, this polynomial factors is x times x minus 1. This polynomial factors is x times y minus 1. And so, in fact, I is x intersect x minus 1, y minus 1. So in this case, these are both prime ideals, and we can see that because when we quotient by this, we just get a polynomial ring in one variable over a field. That's a integral domain, so this is a prime ideal. Similarly, if I quotient by this, I just get the field itself, so these are both prime ideals. And so the zero locus of these two things are, well, here the zero locus of this is just the point 1, 1, so I have the point 1, 1 that corresponds to this. And then here I have, where is x equal to 0? So when x is equal to 0, I have this. So there's my corresponding variety. So the picture is that the primary decomposition of an ideal you can visualize as the corresponding variety. So that's going to be our motivation. But now a module is a more complicated thing. So how do we visualize a module? So this is how we can visualize, how to visualize an ideal. At least an ideal in a polynomial ring is to just visualize its zeros. And we can actually reconstruct, we can go back and forth, not perfectly, because there's some noise that comes from this primary versus prime component, but we can go back and forth at least from this picture of the variety to the associated primes. And so here's a quick example. Primary decomposition is not unique. So if we take xy comma x squared, so this is an ideal in our ring R up here. Let's call this ring R of xy R. This ideal can be written as, on the one hand, it's x intersect y comma x squared. So if I intersect these two ideals, obviously x squared is in there and xy is in there. You can check that, in fact, that is a decomposition. This, when you play around with the definition, you see that these are both primary. On the other hand, we could write it as x intersect x squared, xy, and y squared. And a moment of thought, or 2 moments of thought, or maybe 10 minutes, will convince you that these are also both primary. So these are two distinct primary decompositions. And so primary decomposition is not unique. However, when we pass to the associated primes, when I look at the radical of these, the radical of this ideal is simply xy. And that's also the radical of this ideal. So this goes to what I was saying, that if we have the underlying variety, we can't get the whole primary decomposition, but what we can reproduce is the associated primes. And that's going to be sort of the intuition for us for the next thing, which is localization. So this is the last technical bit of the talk. So I'm going to clean up the blackboard here. I want to keep that example with us. And again, going back to what we're trying to do is our goal is to visualize a module. So, localization. So if R is a ring, and S a multiplicatively closed subset of R, then I can form the localization RS, which is pairs, which I'm going to write as fractions, F over G, with F in R, G in S. And there's an equivalence relation, which I'm going to write F over G is equivalent to F prime over G prime. And it's just cross multiplication. So I'm not going to write that out. But here's the first example of localization, and or actually the most common case is where S is the complement of a prime ideal. All right, second chance for a graduate student to earn a beer. If our ring R, beer prize. Maybe I'll have to up my game and offer wine instead of beer. Is that maybe that was my flaw, my mistake. So beer prize, if R is equal to Z, for the Canadians in the audience, Z's dead, right? So if R is equal to Z, and a prime ideal in Z, well, what's a nice prime ideal? How about P is equal to the 0 ideal? That's certainly a prime ideal. Z is an integral domain. Multiply two things, you get 0. One had to be 0. So the complement of P is, it's everything, right? Except 0, right? So P complement is everything but 0. So what is, for the prize, Z localized at P? And this is the way people usually write it. They put a little loop around it. So Z, P is a familiar object, beer prize, beer prize. I see someone typing. Yes, you'd need more than cross multiplication. I'm being cavalier here. This is localization in 5 minutes, okay? But the analogy is, it's pretty close to that. If I localize at the 0 ideal, everything outside 0 has become a unit. So I'm looking at things of the form F over G. These are both integers. This is a non-zero integer, modulo a certain equivalence relation, which I didn't write out. You can look at, Google localization, and you'll get the right definition.
I think we have a chatted answer. So
we have a chatted answer. John gets a beer. Q, right? It's Q, right? So it's Q. All right. So so this is the most common case. What I want to do now is we're going to use that. So if M, so now here's our definition. I can do the same. So if M is an, let's do def. If M is an R module, then we can make M localized at P is an R localized at P module. And so if we actually do a sheaf theoretic version of this, when I sheafify everything by putting little twiddles over them, again, now I'm glossing over basically a huge chunk of chapter 2 of Hartshorn, for example. I get something called the stock. So this is the analog of a fiber. And this P, I'm only going to do this P for a maximal ideal because there the intuition is it's a point. You can do this for any prime ideal, not just points. So we get an RP module. And so what I want to do is, that's a definition I can localize. And so my point is, for us, if we take, for this, let's take R mod I is an R module for the above example. And now what I want to do is I want to understand what are the stocks of the corresponding sheaf. So what is R mod I localized at P? What is this? What does this look like? Equals, and it's going to have three things. There's three possibilities. And my P, this prime ideal, I want this P to be of the form x minus A, y minus B. So this is corresponding to the point A, B, and R2, right? So this ideal, if we looked at the zero locus of this ideal, it's simply the point x equals A, y equals B. So it's a point. So as a picture, so here's our picture. So this is R2 down here. I want to draw R2 here. And now I want to visualize this sheaf as being something that lives over the various points of R2. So let's see what happens first if we localize at a point A, B, which is not one of our associated primes. Remember, the associated primes were x and x minus 1, y minus 1. So if this is my, x-axis, this is the y-axis, I have sort of two distinguished points. I have the distinguished point sitting here at 1, 1. And then I have, well, not points, and then I have all the interesting points that lie along the, oops, when x is equal to 0. When x is equal to 0, I'm lying along this, right? So that's what that's this picture where I flipped it down here. So this has become this, and this point is now the point right here. So what is this stock? So I claim that if AB, or if our deal P, if P is not equal to either x or x minus 1, y minus 1, that we get 0, that R mod I localized at P equals 0. Why is that? Well, when we localize at P, at this ideal, everything outside that ideal becomes a unit, right? So that's what we're doing. Localization is somehow, and when you quotient by something, you set everything that you're quotienting by to 0. When you localize at a prime, you're making everything outside the prime invertible. So when we localize at P, everything outside this ideal becomes invertible. If AB is not either this point or a point on this line, that means that x is invertible because it's not in the ideal. X minus y and y minus 1, one of these things is not invertible. So one of these is invertible. This thing's invertible. That means either this is a unit or this is a unit. But I'm quotienting by it. If you quotient by a unit, you're 0, right? I quotient by units, so I get 0. So these things. So the point is that at any point over on my, this is my affine plane here. At any of these points, the stock is 0, so I have nothing. But if I localize at the point when P is equal to x minus 1, y minus 1, when I localize at that point, everything outside there becomes invertible. X is not in this ideal. So x is a unit. That doesn't kill this. All that does is it means since x is a unit, I can invert it, I convert it, and I just get the plain old ideal x minus 1, y minus 1. So over the point 1, 1, I just have the point itself. I want to make the distinctions. Over these points, there's nothing. Over this point, there's actually a little point there. And so then the last one is if P is equal to x, well, when I localize at x, neither x minus 1 nor y minus 1 is in the ideal. Therefore, they both become units. And so in this factorization that I had, this is a unit, and this is a unit. So I just get R mod I localized at P is just R mod X localized at P. And so R mod X, if I quotient my ring R by X, I just get R of Y. So what I have essentially is I have a line over each of these things. This is, I'm drawing R of Y as a line. So because I'm thinking geometrically as a speck of that. So the way we visualize this module is as a point and this line. And so the same decomposition, and we've only done this in the simplest case where our module was a quotient like this, but the same general idea works. So I have 2 minutes left. And so the key.
And we started you late, so you have more than 2 minutes.
Okay, so you guys can. Well, people, I'll just see the number of participants start clicking off, right? So,
that's right.
But there's always the hope there might be another beer in the offing, right? So, all right. So I had the last piece of the talk was going to be 5 minutes, and so what's interesting? So the last 5 minutes, the last section. This was section I had it as section 3. Was z to the n graded modules. So a lot of times when we look at the polynomial ring, so if we look at r equals, say, r of x1 through xn, we use a z grading that is something like x squared minus xy has degree 2. We call it homogeneous, because all the monomials that appear have the same degree. So I'm not going to, again, I'm being a little, more than a little, I'm being very cavalier, but the point is that in a z grading, a polynomial is homogeneous if every monomial that appears has the same degree. So dot the degree vector with the vector of all ones. So to z, when we grade with a z to the n, so that's like saying x1 has weight 1, all 0, so this is a vector of n things, xn has weight 0, 1, like that. So a z to the n grading, or sometimes called the fine grading, you put this grading where x1 has weight, call it e1 or something like that, and this is en. So that map, the differentials that we defined, the MPH differentials, are maps of z to the n graded modules. So now, what's amusing is that theorem that I wrote down at the very beginning, which was about multiparameter persistent homology, has this, that such modules are supported on unions of coordinate subspaces. That's really not about multiparameter persistent homology at all. It's about z to the n graded modules. So, and the point is, let me ask you a question now. We said in the ordinary z grading, this polynomial has degree 2, right? This has degree 2, this has degree 2. Is this homogeneous in the z2 grading? In the z2 grading, what's the weight of this thing in z2 for a beer? This is an easy question. Anybody can answer. Moderators can answer.
2-0.
2-0, right? You want to be good job. So that has weight 2-0. This has weight 1-1, right? I mean, the point is that in the fine grading, every single monomial has a different weight. So what are the homogeneous ideals? So question, homogeneous ideals, well, that's not homogeneous ideals. We know that homogeneous polynomial in the z to the n grading is just a monomial. So that means that the only z to the n graded ideals are monomial ideals. So this is a hugely restrictive condition. So this ideal, if I took x squared xy, that is a homogeneous ideal because each polynomial is homogeneous. When you take a homogeneous ideal, not every generator has to have the same degree, but each generator has to be homogeneous. So here's a homogeneous ideal. And so the point is, now let's figure out what are the associated primes, because the support loci, so the point is that if M is an MPH module, what are the associated primes? So I didn't say what the associated primes are of a module. I'll tell you what they are. So P is an associated prime of M if and only if P is the annihilator of M for some M in M. So that's the definition of the associated primes of M. So the point is, when I localize, when I look at the stocks, right? When I look at the corresponding sheaf, when is this sheaf non-zero? What do these primes have to be? Well, we're in this category of z to the n graded objects. That means that these primes have to be z to the n graded. And so the whole thing comes down to a question of, I'm like 3 minutes over, so I stop now. What monomial ideals are prime? Period. Full stop. What monomial ideals are prime? Well, as soon as I have a product of things, I'm screwed. That means the only monomial ideals that are prime, so the point is, the only z to the n graded primes are subsets of the variables. And that means that the associated primes of an NPH module are exactly coordinate subspaces, right? And so that gives you the decomposition theorem. And so that's a good place to stop. Apologies, I went a couple minutes over. Henry, thanks for what do you call it when you grant dispensation? Thanks for granting me the dispensation to go over time. So I'll stop and take questions, and whoever was harassing me about the official definition of localization, I'll write it out right here.
That was Murad. It was Yadin. You owe him a beer as well.
Right. Okay. Murad a beer.
Yeah. So I had a question. So just to complete the dictionary, you know, my primes are, you know, just collections of the variables. I can't have powers or products. Yeah. And so when I have like a y, right? Does that mean my point or line or plane extends in the y direction, or does that mean that it's killed in the y direction?
That's a great question. So it's exactly the intuition that we had for the example was supposed to point the way. So we had our module, r mod I. This ideal was x intersected with x minus 1, y minus 1. So the associated prime lived sort of along the corresponding variety. So this is being killed. So, right, so in the picture, when x is equal to 0, we're along the y-axis, right? And so that you're killing that direction. So you're left with the complement. Is that was the question, right? Yeah, exactly. Yeah. Just like, I mean, I mean, I shouldn't say it that way, but here's an even more sort of simple example. If we did, you know, k of x, y, or r of x, y, z, and then I mod out by x, y, this is saying x and y are 0. So the only thing that's left is the z-axis, which is complementary to the xy plane, right?
Right.
Yeah. But so I do think that this decomposition really it does give you, so your MPH modules are exactly what it's, so in 3D, you have a bunch of copies of all of 3 space. Those are like the free summands. Those are like the long bars. But then you also have a bunch of planes. Those are somehow, they persist, but they're lower dimensional, a bunch of lines, coordinate lines, and then the sad little, you know, point at the origin with some fatness, but eventually, because it went to McDonald's and supersized itself, even though it's fat, it eventually dies, right? So. Other questions? I'm not giving away any more beers. I think I'm in debt for 3, but you have to. So you should email me if I owe you beer. You should email me because I am looking forward to being able to get together in person. Man, I had conferences in Oaxaca and Lumini and Italy, and they're all gone. I hate this.
I had a question.
Yes, Jacob.
Yes, I was wondering if you could adapt this construction where you replace the integers by the real. That is, you're allowed to have a multi-parameter persistence module over R, or R2 or R3. You see what I mean?
A real parameter. So this ties in. You guys should have, maybe Ezra's already given a talk. So if you want, instead of an integer parameter up here, a real parameter, Ezra has worked really hard to develop sort of a theory of graded modules with real parameters. But so I don't know the answer to that, but it's a very reasonable question. And I would say to check out Ezra's work on that.
Thanks. Okay.
It is more intuitive. Somehow it's more intuitive though, right? I understand your point, So again, the thing that I totally glossed, but we all know about MPH, is that or persistent homology, it's like Morse theory, right? So we really have a real parameter. So we've got this epsilon parameter that we think of as our thickening, right? And so, but we cheat, because just like in Morse theory, there's only a finite number of points where the topology changes, right? So we can discretize things. And when we discretize things, then it turns it into just, we only care about Z. It's exactly like Morse theory, right? I mean, it's very analogous to Morse theory, but the wanting to have a real parameter that's there as a real exponent is certainly a reasonable thing.
Yeah.
So I have a question, actually. So in the special case of one-dimensional persistence,
Yes.
in that case, you have these axes and these points. Where is the birth and death time information encoded?
Great question. So it's kind of like a do no harm, right? So if we take this multi-dimensional persistence and we specialize down to just one variable, the birth and death with graded modules are generated in a particular degree. So I might have, k of x, here's an example. So k of xy, I can think this is a free module, right? But I can actually, if I think in the graded setting, I might have the ideal x squared. So x squared is a free module, right? There's no relations on this, but it's generated in degree 2, right? So the point that I completely ignored here was that in this graded setting, all of these modules, because they're graded, will come with a generator degree. So you're not always generated in degree 0, right? So they're generated in a certain degree, and then they're annihilated in a certain degree. So just like in a Z module, so I might have, and so in the one parameter setting, R of x, we really have the free sum ends are going to look like a bunch of, so x to the, they'll be generated, I'll have something like a direct sum, I equals 1 to m of x to the ai times r, right? So these are my free sum ends, and they're generated in a specific degree, but then they live forever. And then I'll also have a big direct sum, j equals 1 to n of r of x to the bj r. So these are generated, there's my birth, I guess I should, well, whatever. There's my birth degree, but then it's modulo x to the bj plus dj or something like that, right? So, and it dies. And so this is a graded module in one variable. When we're in the Z2 setting, or Z2 grading, then this would be something like x to the a, y to the bi, r, and so on, right? So I'll generate it in a certain degree, and I'll kill it in a certain degree.
So just a kind of follow-up to that question. So suppose I give you a persistence, say, bimodule, and you pass it through all this algebraic machinery, and at the end you hand me back, say, some data structure that will encode the information. What would a data structure be, or what could a data structure be that encodes this, which somebody who maybe isn't as familiar with the algebraic machinery, they could make sense of?
I think the nicest way to encode this was, and I said very, very roughly, but it's closely analogous to a barcode. So it would be something like, let's just do it for 2 parameters, right? So I would have a certain number, so I would have something that looks like this. I would have a direct sum, I equals 1 to n, of x1 to the ai, x2 to the bi, times r. So r is now going to be r of xy. So these are our persistent, these are our full dimensional persistent components. And then we'll have something that looks like direct sum I j equals 1 to p of x 1 to the ci ck x2 to the pj r modulo. And now what's going to happen is I'm going to kill off something that looks like either x, let's say x1 to the cj plus ej or something like this. So this is a fattened component where I'm killing, right? So this is going to live, I'm killing the x1 direction. So this is something that would live along the x2 axis, but it's been fattened. It's translated and fattened. So there's, again, there's a birth degree and there's a death degree, but the death degree only kills one variable, right? And then I'd have a similar thing, same for x2, where I just replace that. And then I'd have my last little, so these are persistent components. These are persistent components that live forever, but not full dimensional. So I call these 1D persistent components. And then we'd have something that looks exactly like the x to the I, or x1 CD. I've already used D. Let's say, I don't know, Z I x2 to the yi or something, r modulo. But now this ideal is going to have two things because I'm killing in both directions. So I'll kill the x and the y. So this is the thing that's going to be supported only at the origin, but it's somehow, and it's not necessarily fat in the same directions. It's generated in a certain, it's born in a certain degree, but then it dies. Maybe it's sort of somehow fatter in one direction and skinny in another direction, but it really is concentrated there at the origin. And so again, when you look at, the point is that when you look at the associated primes, the associated prime for this is just going to be x1 comma x2, right? Because it really only lives at the origin. The associated prime for one of these things is going to be in x1. The associated prime for this is going to be in x2. And then there are no associated primes for this because this is a free module. So that would be the data structure that I would use, is this data of where is the module generated and where do the generators lie, right? And it's all, but the point is that it's all just about coordinate subspaces. So there's really a very small finite data set. I mean, it's not quite as nice. You can't really draw it as a barcode, but you almost can, I think. So at least in 2D.
At the risk of being obnoxious, I'll ask one follow-up question. Do you think this is a complete invariant for something that is simpler and faster to compute than multi-parameter persistence? Because if we're anyhow throwing away information, maybe we didn't have to compute everything to begin with.
I would be surprised. It depends. So it depends on how much simpler the thing is. So in certain, I mean, I guess what I would say is, yes, if you simplify the shit out of something, then you'll probably get to a place where this is a complete invariant. So that, I mean, which is that's a crappy answer, but it's true, right? So, and you know, it's not actually a crappy answer because there are certainly lots of situations where you can say, well, I'm only interested in this particular type of situation. So let's make some simplifying assumptions so that we can actually do something, right? So, so yes, I believe it would be in certain situations. I believe it will be in certain situations. For example, here's a stupid situation. Suppose your module decomposes itself directly, then you're done, right? I mean, that's it, right? If you know it decomposes. So.
Thank you.
I had another question if you'll humor me. So take this however you will, but I sort of see multiple lines of work in multi-parameter persistent homology, and some is more based off of this pre-existing machinery coming from algebra, algebraic geometry, and that's where I would sort of put this talk a little bit. And then other work is much more concerned with, say, the stability of persistent homology. And I'm just curious what your impressions are of that. So in some sense, you're ZN, so people don't really talk about interleavings, but from another perspective, you can, like ZN is really just like a small discretization. And so you can talk about epsilon interleavings where epsilon is small compared to that.
Henry, I think it's great. I think it's a great question. So, and you know, to be completely candid, I got interested in this because I think this is, and for the grad students out there, here's the avuncular, or maybe not avuncular, grandfatherly advice is when you go to a talk, you should be hunting. You should be like a hungry hunter, and you're looking for targets where you can actually make some progress using the machinery that you already know. So that, in a sense, it's exactly what you said. So here's this, approach of Carlsson-Zomorodian. They ask a question. I think this is actually a really nice, clean answer to their question. Whether it's actually useful. So that's the other question, and that's our flaw at least, I don't know, maybe I'm not a pure mathematician anymore, but I think too many times pure mathematicians look at an applied problem and they try to shoehorn it into the existing machinery, which is exactly what this is, right? But that maybe doesn't answer. And the question is, how useful is this? Well, as I said it, and I did at least offer a disclaimer, which was, we're starting with a filtered simplicial complex. Well, you know, a lot of the hard work is going from the point cloud data to get that filtered simplicial complex. Once I'm there, I'm already, you know, I've discretized everything. I'm happy. So I think that, I guess going back to the specific question of interleaving, I think that the questions that are coming from the folks who are actually working on the computations and trying to apply it to real data, those are the significant questions, I think. And so the real, I guess, maybe a takeaway is, how do you marry those two, or how do you put them together in a way that combines the best of all possible worlds? Of course, Ken found out that the best of all possible was not necessarily so good, but anyhow, that was a rambling answer, but yeah.
Before we give a sort of applaud the speaker, I just wanted to ask, could you tell everybody, is there some resource, some paper online for people who want to learn more about this work?
Great question. So all of this, so this actually, everything I discussed today was published last year in the SIAM Journal of Applied Algebra and Geometry. It's joint work with Heather Harrington, Nina Otter, and Ulrike Tillmann. I think we do a pretty careful job of presenting everything, exactly because of this fact that I think a lot of the algebraic tools are not something that would be standard in a toolkit for an applied topologist. So that would be a good resource for that. The other thing, if you wanted a, so here's a pitch. I actually taught a course in June on topological data analysis with the goal of understanding multiparameter persistent homology. So it's a much more leisurely, in fact, it's 8 lectures. It's online on my website. And there's a set of notes there too. And this was taught actually to graduate students. The audience was graduate students in statistics. So I worked really hard to make sure that I went through the algebra and the topology rather carefully. So there's a bunch of notes there, which are my handwriting. Well, you guys have seen the problems with the handwriting, but that's someplace else that you could look if you are bored and restless and want to watch more stuff online instead of going out and and being outside. Oh, and remember, all of those of you who are in postdocs and going to be on the job market, keep your eyes on math jobs. So, and I will send. Henry gave me some websites for advertising, so it'll appear there too.
Brilliant, thank you. Okay, so before we wrap up, could everybody please unmute yourselves and applaud our speaker?
Thanks, guys. Look forward to seeing everybody. And like I said, buying beers. Maybe I'll buy everybody a beer. You know, who knows? All right.